Interpreting proton NMR spectra offers an excellent opportunity for you to create your own system for organizing and interpreting data. As there is no set order in which chemical shift, multiplicity, and integration must be analyzed, you may develop your own approach as you solve NMR problems. So what I'm going to talk about is a starting point for solving a structure from the proton NMR. And in this method, the data is tabulated, and then chemical shift and integration data are combined to propose small fragments or pieces of the molecule, which are then linked together using multiplicity information. So it's not ever going to be possible to solve all of the structures with this procedure, but we can solve many of them. All right, so we have a molecule that has, and we don't know the structure of it, it has the molecular formula C6H12O2, and so you can see all 12 of the protons on our proton NMR, 6, 7, 10, and then 12. Okay, and there's 4 different types of protons. So the first thing that we're going to do is we're going to gather the information that we can from the molecular formula or other information. So if you have the IR, it's also helpful to refer to that. Maybe mass spec is also useful to you. So make sure that you use all of the data that you have available to you in your structure determination. It will make your task simpler, and also the final structure does have to be consistent with all of that data. So we know that the formula for this molecule, perhaps there's the mass spec or something that we got that allowed us to figure out the formula. It's C6H12O2, and so that tells us that there is 1 degree of unsaturation, and of course there's 2 oxygen atoms in this molecule that we can't see directly using the NMR, but we know it's there. We know they're there. So the first thing that we want to do here is, with our spectrum, is to actually tabulate our proton NMR data. And so the center of each signal, in other words, like right down the middle, is the signal that we record in the table. And then the integration and multiplicity are also tabulated for each signal. So for instance, at 0.9, we have a signal that is for 6 hydrogens, 6 protons, and it has a multiplicity that it's a doublet because there's those 2 peaks there. Okay, and so at 1.8, remember it's the center of each signal that we record in the table, and it has an integration of 1. And the multiplicity is a septet. I think it might be even more, but we'll just go with the septet for now. So this is the same table. I've just transferred. It's just now all on a white background instead of having the different columns and rows being different colors. So it's the same information, just transferred it to the next page. And so now what I'm going to do is I'm going to assign the structure of each fragment. So the doublet at 0.9 parts per million arises from 6 identical protons, and we know that because of the integration, and that's in the methyl region of the spectrum from the chemical shift. And so we need a correlation table to do this. If you have your NMR correlation table, you can go ahead and refer to that. There's one in Klein, etc. All right, so the multiplicity of this signal is it's a doublet. And remember, multiplicity equals the number of adjacent hydrogens plus 1. So that means that there are 6 identical protons next to 1 proton. Okay, and so it's possible that you could have like I don't know, maybe you could have CH3s bonded to separate carbons, but they're all identical. So whenever you see this 6 and a doublet, it's very likely that you're going to have 2 methyl groups bonded to the same carbon, and that one carbon has a hydrogen or proton attached to it. Okay, so the septet at point 1.8 is from the, there's an integration of 1 and it's split into 7. So using the multiplicity rule, that means that one proton is next to 6. So that's just this other proton right next door, right here, right there in red. Okay. So then we have a singlet at 2.3, and that's 3. It has an integration of 3. And it's next to a carbonyl, and we know that because of the chemical shift. And I'd say this is the easiest thing to forget about because you really do want to refer to a correlation table to sort that out. But don't forget about your chemical shift data because it will tell you the chemical environment of your proton. And so this is deshielded because of this carbonyl. So we have an integration of 3. That's the 3 hydrogens bonded to this carbon. It's a singlet because there's no hydrogens next door. And from the chemical shift, we can see that this methyl group must be next to a carbon, or next to a carbonyl, pardon me. So the doublet at 3.8 parts per million is deshielded, right? It has a chemical shift in the range expected for a proton adjacent to an electronegative oxygen, which we know we have in the molecule. So there's an integration of 2. So we assign our 2 hydrogens as being on a carbon that's bonded directly to an oxygen. And since this is a doublet, using our multiplicity rule, it means that it's adjacent to a carbon with 1 proton bonded to it. So now what we do is we put our fragments together. And so one of the things that I think is useful to do is to look for the terminal fragments. In other words, kind of like the edges of the puzzle or the corners of the puzzle. And so the CH3 groups here, this is a terminal piece. There's nothing else bonded to these methyl groups. And so we'll put them on one end of the molecule. On the other end of the molecule, we have the methyl bonded to the carbonyl. Again, you can't bond anything else to this methyl group, so it has to be the end of the molecule. So those are the 2 ends of the molecule. We know kind of stepping one step and then the next step that the 2 methyl groups are bonded to the hydrogen. And now we can invoke this or bring in this final signal down here. We see that if you have 1 hydrogen in those 2 R groups, hydrogen, and those are the 2 R groups there, then that's bonded to a carbon bonded to 2 hydrogens. So this carbon right here, it's bonded to 1 hydrogen, and it is next to the CH2 group that's bonded to the oxygen. So we've pretty much used up all of our carbons, our 6 carbons and our 12 hydrogens and our 2 oxygens. The only thing that still needs a bond to it is this carbonyl, and so we just connect those 2 fragments together and our molecule is finished, and we wind up with that isobutyl acetate.